Hi, today I'll be presenting the Liquipedia Calendar. Liquipedia Calendar is a software that allows users to view upcoming events in the eSports scene without installing any application. The calendar is updated in real time and provides information on tournaments, matches for your favorites players, and video games. It also provides some details on the match's format, name, and opponents. Assuming Liquipedia itself has correct information, you will never miss any finals anymore. To get started, you just need to click on the website link in the description of the repository on GitHub. It will lead you to a Next.js statically generated website where you can put links to your favorites players to track. If you open liquipedia.net in another tab, you can access your favorite player page and copy the URL. Then you can paste the URL in the input field and press either space or enter to add the player to the list. You can also remove a player by clicking on the tracked player element that was just added. Once you are done, the generated URL is automatically copied to the clipboard, so you just need to click Add to Calendar. That was all. Now your calendar has an automatic update of the matches of your favorite players. Liquipedia Calendar uses liquipedia.api to get the information about the matches. The website is made using Next.js and TypeScript and is hosted on Liquipedia Calendar GitHub pages automatically after each updates through continuous delivery. The Calendar API is made using Go and is hosted on Google Cloud Platform on App Engine. That choice is justified by economics, as the F1 instance can be free forever and because it provides a free memcached service. When a service like Google Calendar asks Liquipedia Calendar for updated data, the first request will be a cache miss. That will trigger an API call to liquipedia.net and parse the response as HTML, filter out the players that aren't tracked, and finally return the calendar data. Due to the external API call, that request is slow, can create load on APIs that I don't own, and move a lot of redundant data. To mitigate that, the API will cache the request to liquipedia.net, which has a game for key. There's about 24 of games, so it stores all the events for a single game in a single cache entry, which won't break space available in memcached. The entries expire after some time to update the events. Finally, as the esports scene is superstar heavy, it is beneficial to cache the request for a specific player as well if it's popular. That way, instead of having to parse the game cache and filter out players for each request to that player, the API can just return the cache data directly. To benchmark correctly the application, we must remember the correct cases. The important ones are cold start, warm start, cache miss, game cache hit, superstar player cache hit. A cold start is when no pod is currently running. It happens since we use App Engine horizontal pod autoscaler. A cold start basically need to start the Docker image. On the measurements you can see, a cold start have nearly 1 second of latency, with 60 milliseconds to 120 milliseconds of latency from request to response, which is expected due to the API call. The game cache hit on warm start reduced the request to response latency up to 6 times, as the only processing left to do is parsing HTML and filtering. Finally, the superstar player cache hit reduces further the latency down to a few milliseconds, which is almost identical to the 404 return case on bad request. It means we reach the maximum theoretical speed for our popular case. The application is also using Google Cloud Logs to monitor real-time usage and issues, as well as enable benchmark-driven development. As you can see, the numbers are easy to produce. On DevOps side, GitHub Actions enable continuous integration and delivery by automatically testing the application's features and deploying the website to Google Cloud Platform. Regarding the latency requirement, it is important to note that we do not actually require low latency for a good user experience, but for performance reasons only. The reason for that is because the calendar service the user uses won't notice the latency anyway, as long as it doesn't time out. As such, our only requirement is to not time out, which means that under high load, we need a fast service, and under low load, we can afford having the HPA configuration set to a minimum of 0 instances, which implies a possibility of cold start during operations. All of that contributes to a low financial footprint, which is the only way to keep that kind of services running sustainably.